Hi, and welcome to section 2.5 in your book. 2.5 talks about identifying lone pairs in terms of looking at a bond line a drawing and being able to see a charge and know how many lone pairs are present on an atom. This is really important because in bond line structures, they are not required to always give you um, how many lone pairs are there, but they are required to say what the charge is. So you need to be able to look at an atom and be able to know what the charge is, or what the lone pairs are on that atom. So what you need to know to do this simply is first to be able to know the formal charge um, equation that we did that we learned before, and you have to remember that the formal charge is equal to the valence minus the non-bonding electrons minus the bonding electrons over 2. Okay, so now that we know that, then it becomes a little simpler because let's take, for instance, let's take a molecule like isopropyl alcohol 2-propanol with, oops, sorry, with a negative charge, often circled like this. So to find how many non-bonding electrons that it has, what we need to do is solve for n, right? The non-bonding electrons, because what we know is that the formal charge is -1, based on the minus drawing there. We also know that oxygen has 6 valence electrons. We're solving for n, and we know that it has 2 bonding electrons. There we are. So now that we know that, it becomes a little simpler to say what the number of lone pairs is, because we can just solve for it. So let's do that. So in solving for it, we just simply do the math. So that's minus, sorry, minus 7 is equal to negative n. Man, my tablet is messing up. Minus 1. There we are. Okay. Y. There we go. Okay. And then, let's see, minus 6 is equal to minus n. And from there, all we need to do is say that 6 is equal to n. All right, and then and that's how we solve for the lone pairs from the formal charge. And what we can notice is that when we do this, the oxygens in general, when they have one bond, like that, and a negative, will have 1, 2, 3, 4, 5, 6 non-bonding electrons, so 3 lone pairs. An oxygen with 2 bonds and a zero formal charge, a formal charge of 0, will have 2 lone pairs, and an oxygen with 3 bonds and a positive charge will have 2 lone pairs. And we can find that out from the same exact equation. I'll leave it to you to work that for yourself. Now, oxygen isn't the only atom that has this similar -1, 0, +1 relationship, because if you notice, each lone pair, say here, say here, um, gets lost with the addition of a new bond, because that's where the new bond is being formed. This one goes to be that carbon eventually, right? So in making bonds, you're using lone pairs. So you can tell from the number of lone pairs or for the number of bonds and the charge what the number of lone pairs should be. So similarly, if we were to look at nitrogen, there we are. If nitrogen has 2 bonds and a negative charge, it has 5 valence electrons. So then it must have 2 pairs of non-bonding electrons. Similarly, a nitrogen with 3 bonds, 6 bonding electrons, and a charge of 0 has 2 lone pairs, and a nitrogen with 4 things bonded to it, that is 8 bonding electrons, and a plus charge has 0 lone pairs. You see how oxygen went from 3, 2 to 1, nitrogen went from 2 to 1 to 0, and carbon goes from 1 to 0 to having a full positive charge, or an empty orbital. So carbon goes from having, there we go, 3 bonds and a negative charge there. That means it has 1 lone pair, a carbon with 4 bonds, and no charge, has no lone pairs, and a carbon with 3 bonds and a positive charge also has no lone pairs. So we can work more of these. I'll hopefully post some practice problems later so you can see this more in detail. But this lets you know kind of how to find the number of lone pairs from a charge given to you in bond line drawings. This has been section 2.5.